Hello dear students. Welcome to the world of nuclear technology. Hello dear students. Welcome to the world of nuclear technology, scientific breakthroughs, and sustainable development. My name is Maria Tserina, and I'm a leading specialist at the Mathematical Modeling and Digitalization Department of Prarif JSC. The Prarif, or Breakthrough Project, creates the future of nuclear energy. And that's what we are going to talk about today. I will also tell you how to look into that future. No, not with magic crystal balls or spells, but through science and technologies. But before we travel into the future, let's look at the present. What nuclear energy looks like today. Modern nuclear power plants provide humanity with clean, stable, and affordable energy. Nuclear energy doesn't depend on the weather, it operates in various climatic conditions. One of its main advantages is the enormous energy density of fuel. Just imagine, 1 gram of uranium gives as much energy as about 2.5 tons of coal. During operation, a nuclear power plant does not emit greenhouse gases into the atmosphere, and over its entire life cycle, from uranium mining to waste disposal, and nuclear power plant CO2 emissions are lower than from solar panels or wind turbines. But even such significant advantages over other energy sources do not mean that nuclear energy should rest on its laurels. On the contrary, its huge potential requires constant progress. Today, the industry faces a few natural barriers that it must overcome on its path to a bright future. The reserves of natural uranium-235, which fuels thermal reactors, are not infinite. According to various estimates, it will last for 60 to 150 years at current consumption levels. Therefore, we need to find a way to expand the resource base, for example, to use the much more common but less active isotope uranium-238 as a fuel. The Prairie Project is the answer to these challenges. Its goal is to create a new generation of nuclear energy based on the principles of inherent safety and competitiveness. The main idea is a closed nuclear fuel cycle with fast neutron reactors. More than 2,000 specialists from over 60 organizations are working on the Prairie Project. The project is currently in the active implementation stage. In Severs, Tomsk region, a pilot demonstration energy complex is being built. This complex will demonstrate the closure of the nuclear fuel cycle. Now, let's pause for a moment and talk about nuclear fuel cycles. There are two types of such cycles: open and closed. The outer arc in the diagram shows the open nuclear fuel cycle, the traditional chain from uranium mining to spent fuel storage. The inner circle with green arrows shows the closure of the fuel cycle. Unlike the open cycle, here spent nuclear fuel is not sent for long-term disposal, but is reprocessed to extract available fissile materials, which are then reused to produce new nuclear fuel. Radioactive waste is minimized and the resource base becomes almost limitless. Fast neutron reactors can produce new fuel not only for themselves, but, if necessary, also for thermal reactors, and can also burn uranium from spent fuel left by their thermal elder process. This is called a dual-component nuclear power system. The closed nuclear fuel cycle has many advantages. First, it's a new level of safety. The very design of fast neutron reactors reduces the risk of accident to a record low. Second, it provides technological support for the nuclear non-proliferation regime. Third, it makes full use of the energy potential of uranium, and it's economically feasible. A closed cycle makes nuclear energy truly sustainable and virtually waste-free. This is not science fiction, it's an engineering reality that the Prairie Project is creating today. At the very beginning, I promised to tell you how to look into the future. And now we come to the most interesting part. How can we be sure that a complex technological system will operate reliably and securely even before its actual launch? How can we see a potential problem long before it might occur? The answer is digital twins. A digital twin is not just a beautiful three-dimensional model. It is a virtual representation of a real-world object, system, or process. Digital twin is updated with real-time data, which can be used for machine learning and reasoning to make better decisions. We can study all sorts of potential situations, analyze performance problems, and create potential enhancements. That can be used to improve the real physical object. Digital twins are designed around a two-way flow of information that occurs when the object sensors provide relevant data to the digital twin, and then that happens again when the insights created by the digital twin are shared back with the original source object. And since digital twins are meant to mirror a product's entire life cycle, it's not surprising that digital twins have become widely used in all stages of manufacturing, getting product from the design stage to the finished product and all the steps in between. Prarif is using digital twins to look into the project's future. Now, let's take a look at it. This is the Pilot Demonstration Energy Complex. It consists of three main parts. The first is the SPAD fuel reprocessing module. The second is the fabrication refabrication module, where fresh fuel is made from reprocessed materials. And the heart of the complex is the reactor unit called REST. This is a fast neutron reactor with lead coolant, one of the safest and most promising in the world. All parts of the complex are brought together on the same site for the first time in history. The digital twin of the Pilot Demonstration Energy Complex consists of databases, computer, mathematical, and simulation models, as well as design documentation, requirements, and real-time data. Since the digital twin evolves in parallel with the physical object, the fabrication refabrication module currently demonstrates the highest level of maturity among all components of the digital twin. By the time the construction of the complex is completed and the power unit produces its first portion of energy, its digital twin will have already prevented equipment failures, saved millions of dollars, and become a new global standard. The Prarif project is not just a step forward, it's a leap into a new era of nuclear energy. Safe, efficient, and virtually waste-free. Thank you for your kind attention.
Dear friends, good afternoon. My name is Yuri Sestunov. I am the Chief Technology Deputy of the Composite Division of Rosatom. My educational background is composites, and my work is related to the creation and implementation of the composite materials and technologies. Today, I will tell you what composites are, where they are used, and why these materials are opening up new opportunities in aviation, space, energy, and construction. State Atomic Energy Corporation is actively developing new business areas beyond its core nuclear energy production and technology chain projects in nuclear medicine, wind energy, additive manufacturing. One of Rosatom's key strategic priorities is the introduction of advanced materials and cutting-edge technological solutions based on carbon fiber. Today, Rosatom Composite Division comprises 17 manufacturing plants and its own advanced research center, which develops new materials, including those based on carbon and glass fiber. We don't simply produce composites, we are creating the technological foundation for Rosatom's future products in new industries for corporation. Today, based on independently developed technologies, the production of advanced composite materials and fibers meeting the highest global standards has been launched. Domestic technologies for advanced materials and fibers, matching the best international counterparts, have been developed. However, we face ambitious goals, scaling up production and entering international markets. We want to join the group of global technological leaders in the composite industry. Carbon fiber is believed to have been synthesized by Thomas Edison in 1879, while he was working on the light bulb. The modern era of composites began when scientists developed plastics. Before that, the only sources of adhesive and binders were natural resins delivered from plants and animals. In the early 90s, plastics such as vinyl, polystyrene, phenol, and polyester were developed. These new synthetic materials outperformed conventional naturally delivered resins. However, plastics alone could not provide sufficient strength for certain structural components. Reinforcement was required to provide additional strength and stiffness. Engineers soon realized that composites offered not only lightness and strength. For example, fiberglass composites were found to be transparent to radio waves, and soon this material was used to protect electronic equipment. In the 1970s, the carbon fiber that we know today was developed. Today, it is almost impossible to imagine any industry where composite materials are not used. Composite materials, or simply a composite, is a material consisting of two or more components, each with different physical and chemical properties. When combined, they create a new material or improve the properties of one of them. The properties of composite materials depend mainly on the physical and mechanical properties of the components. The matrix gives the composite its shape and monolithic structure. The properties of matrix determine the material's performance characteristics: operating temperature, density, specific strength, fatigue resistance, environmental resistance. Reinforcing fillers are introduced into composite materials to increase strength, stiffness, and plasticity, as well as to modify electrophysical and thermophysical properties in the different directions. There are many different types of composite materials. The diversity comes from different factors. The reinforcing filler in the structure of composite can be arranged randomly or oriented. Oriented reinforcing fillers are classified into unidirectional or two-directional. The most widely used composite materials in engineering are those reinforced with high strength and high modulus continuous fibers. Polymer matrix composites based on thermosetting, epoxy or polyester, or thermoplastic can be reinforced with glass, which is called fiberglass composite, or carbon fiber reinforced with plastic, organic or inorganic fibers. Also, metal matrix composites do exist based on aluminium, magnesium, copper, titanium, or nickel alloys, reinforced with boron, carbon, or silicon carbide fibers. Carbon-carbon composites consist of carbon matrix, which is reinforced with carbon fibers. Ceramic matrix composites reinforced with carbon, silicon carbide, and other heat-resistant fibers. The comparison between composite materials and traditional or classical materials brings us to the main advantages of composites: high specific strength and stiffness, or specific models of elasticity, corrosion resistance, fatigue resistance. Let's talk a little about carbon fiber. Today, there are three main types of raw materials for the industrial manufacturing of carbon fiber. The first is PAF, polyacrylonitrile. Second is pitch, petroleum or from coal. Pitch-based carbon fibers usually have a high modulus of elasticity. However, this fiber is quite expensive, and its manufacturing process is very labor-intensive. Rain-based carbon fiber has lower properties, but some very specific applications. Carbon fiber manufacturing process is multi-stage. It consists of several steps. First step, we take white fiber, PAN, and treat it with the high temperature from 200 degrees to 300 degrees in the air atmosphere. At this stage, we get intermolecular cross-linking, and fiber becomes black. After this stage, fiber is not melty. On the next step, we treat fiber with a very high temperature up to 1500 degrees. At this stage, we call carbonization. At this stage, all the rest atoms leave the fiber, and we get carbon fiber itself. Carbon fibers are used to make fabrics and prepregs, a separate category of materials. Prepregs, a semi-finished product where the reinforcing filler is pre-impregnated with a binder. The most common types of binders used in prepregs are the epoxy resins. Because of epoxy resin used to make prepreg is living material, it is not cross-linked. We have to keep the prepregs with the low temperature, up to minus 18 degrees centigrade. The advantages of composites are widely used in various high-tech sectors of global industry, increasing the competitiveness of finished products. In nuclear, hydrogen, wind energy, development today is simply impossible without composites. Modern high-speed trains, electric vehicles, fuel, gas, and hydrogen tanks for transportation are impossible without composites. Here I would like to highlight three main directions of the industry development. First, getting digital twins of composites and digital twins of the composite technologies. Second is recycling. And third is reducing the cost of carbon fiber and the cost of carbon fiber conversion technologies. According to the experts, the next step in the composites will be driven by reduction of the price for carbon fiber and the price of the carbon fiber technologies 10 to 20%. This slide shows some interesting facts about composites. Just I would like to say that composites, especially based on carbon fiber, is the next step for the space exploration. Spacecrafts and space technologies building in space is not possible without carbon fiber and without composites. So what is the future of composites? First, I would like to underline that composite technologies, materials for composites, will become friendly. Composite technologies must become faster. Carbon fiber must become less expensive. The technologies of manufacturing must be more accessible. A day will come when composite technologies will be as affordable as the home 3D printing now. I wish that if you go into the technical development, sooner or later you will do something for composite development as well. I wish you good luck and have a good trip.